All right, you have a problem on your worksheet that is kind of similar to this one, and it's another kind of abstract type of problem where you're trying to find the point on some given line or curve for which you're given an equation that is closest to some other point. And I'm not going to go through an example that's like with any specifics. What I want to do instead is I want to talk about the abstract approach to how you would solve this problem. And so I'm going to kind of I'm going to walk through like the steps you should take to solve this in generality, and then leave it to you to kind of put in the details and finish it up. All right. So this is I think seeing something in generality in a more abstract form and then applying the abstract idea to the specific scenario, that is like what math is all about, right? That is sort of the core, like that's the core thing that mathematicians do. So yeah, let's practice that here. So first of all, let's draw a diagram. You've got some function, y equals f of x, and that describes a curve. So there's a curve. Let's just say that's y equals f of x. If I ever teach Calc 3, and if you're ever in class with me, you will draw me. This is just my standard. If I need to draw a curve, I draw that. It's sort of like generic curve that is unspecified. For some reason, my hand always wants to make that shape. So there's a curve, and then there's some point, right? We want to find the point on that curve that's closest to some other point, AB. So let's assume AB is the point over here. If AB was actually on that curve, then this would be a boring problem. So we're going to draw that assuming that AB is not on that curve. So now we've got to find the point that's closest, right? So where is it? I don't know. Is it like over here, or is it maybe over there, or is it over there? Wherever the point is that we find, it's going to be on this curve. So I'm going to say it's over here. That point is going to I'm going to label its coordinates x comma y. Okay. And then the actual quantity that we're trying to optimize is the distance. We're actually trying to find the minimum value of the distance between those 2 points. Okay? So there's no particular, so there's constants a and b, right? It's x and y are variables, and then d would be a variable. And d is the thing we're trying to optimize. So now, step 2, let's get a primary equation. Since we're trying to find the optimal value of d, let's get d. So for this, we need to use the distance formula. D is going to be a big square root of a difference in x values. I'm going to write x minus a squared, and then plus the difference in y values, y minus b squared. Remember, the square root and the squares cannot cancel each other because of the addition. You can't distribute the square root over the addition. So that's the distance formula. It doesn't really simplify at all. And that function is a little bit annoying to differentiate because it's got this big square root over the whole thing. So I'm going to give you a tip. D is going to be minimized, which is our goal here, closest to this point AB. So closest means smallest, minimum distance. Let's make that explicit. All right. So D is minimized when D squared is minimized. Ooh. So the reason for that is that if you graph D versus D squared, it's just like, like that, right? It's like x squared. It's just a parabola. And x squared has a minimum value down here, which is exactly when D is going to have a minimum value, right? Like 0 or whatever. So the distance and the distance squared are both going to have a minimum value, not necessarily equal to 0. That picture might be a bit misleading. But the distance and the square of the distance are both going to have a minimum value at the same time, which the minimum values won't be the same. One of them will be the square of the other, but at least we're going to be able to figure out what point produces the minimum value by looking at the square of the distance. So we're going to pick another letter. I'm going to go with C. Let C equal D squared. which if you square the distance, you cancel out the square root, and you just get this, which is going to be a lot easier to work with, okay? So, so now let's try to minimize the value of c, right? And whatever x and y we get that minimizes c is the same x and y that's going to minimize the d value. So now step 3 is to figure out a secondary equation, okay? Let's figure out a secondary equation. The secondary equation for this is the constraint. Now the constraint has to do with what points xy are possible. And the constraint is that xy has to be on this curve. Okay, that's the constraint. So the constraint, the secondary equation here, let's write it down, second equation, that's just y equals f of x. That's it. That's all the secondary equation is. So then, in step 4, when you're doing the substitution, we're going to take our c value we've got, and we're going to replace the y with f of x. So instead of y in here, we're going to have f of x minus b squared. And what you can see here now, this gives us the c value as a function of x only, because here's x, and there's f of x, so this is now an expression of x. And then a and b are constants, right? A and b are some number, some coordinates that are given to you. So so those aren't variables. So this is now the function you can work with, and you want to minimize that. Now, for the for 5 domain, kind of depends on your f of x. Right? It depends on the domain of f of x. Like whatever the domain you should use is just the domain of the function. That would determine what x values are reasonable. So, I mean, it might be all real numbers, or maybe if f of x is like a square root, then it might be is like 0 to infinity, or whatever. So it kind of just depends. And step 6, critical numbers, is also going to depend heavily on f of x. And step 7, obviously. So there's really not much more I can do in generality here. So this is where I'm going to leave it. I'm going to stop here and let you kind of fill in the details here and figure out how to do this problem and how to finish it out. Okay, but I think what I've shown you here is a good template for approaching the problem, and I think I've tried to like explain the idea. And what you're going to do here is find your x value that's going to minimize this c function, and then that will tell you the coordinates of the point, which also is going to minimize the d value. So there you go. If you have any questions, let me know.